Mustafa Amin, who has honored us by being here today with us. So we will talk about the spin-off wave dark matter. A little bit about him. He's now an associate professor at BRAC University. He did his PhD from Stanford University and he's post two postdocs from MIT and Cambridge. And now he's here with us at BRAC University to enlighten us on his research topics. So let's have a round of applause for Dr. Amin.
Let's start off. Okay. So I want to tell you a little bit about dark matter today. And before we get started, let's just say what this stuff is that I want to talk about. So it turns out that over the past century, we found that more than 80% of the matter in the cosmos is not stuff that you, I, or the stars is made up of. The big picture question is, what is the stuff that is not available to atoms? If somebody were to come and tell you that, okay, most of the stuff in the universe is not made up of atoms, obviously you need some evidence for that, and you're just not going to take it at face value. So what I'm going to do is provide a few bits of evidence that astronomers and physicists have collected over the past century regarding this mysterious stuff called dark matter. Okay, so let's start a little bit with a historical look. In the 1930s, Fred Zwicky was looking at how galaxies were moving around. So he was looking at a collection of galaxies called the galaxy cluster and was looking at the speed at which these galaxies were moving around. What he observed was these galaxies were moving around much faster than what he expected. The way he had an expectation was he was looking at all the galaxies, calculating how much mass there is based on what he could see. Based on that, he calculated the speed using Newton's laws. He tried to figure out the speed at which these galaxies should move. And it turned out the galaxies were moving a lot faster. This made him hypothesize that perhaps the reason these galaxies are moving faster than expected is because there is some more matter there that we cannot see that is causing this stuff to move faster. And he gave this extra stuff that he could not see the name dark matter. So this was sort of the first evidence of dark matter. Fast forward a few decades, and there are Rubin and Ford and others. This time they were looking at galaxies themselves, not the motion of galaxies in a cluster, but individual galaxies. And when they looked at how stuff was moving on the outskirts, the outer region of these galaxies, again they found that the way stuff was moving in the outer regions of the galaxy was much faster than what they expected. One could explain this fast motion, once again, by hypothesizing that there's more stuff there that we cannot see. Again, this potentially was the same dark matter. As if this wasn't enough, you move forward a couple of more decades, 3 more decades, and you will get to this amazing observation of what is called the bullet cluster. How many of you have seen this image before? Okay. So this is an amazing image. What you are seeing is 2 giant clusters of galaxies, and many galaxies inside them that are crashing into each other, and we saw this crash in action. So you see that the bright colored stuff is the light that is emitted by the gas in these clusters. You see the bullet-shaped thing, something passing through that looks like that? That's the reason for the name of the bullet cluster. Why was this important for dark matter? It's because if you look at the blue-colored stuff, which is supposed to be a representation over most of the dark matter is supposed to be, you notice that that stuff is at a different location than the stuff that is emitting light. So this is the first time we sort of observed that not only was there more matter, but it was not centered at the same location that visible matter was. So this was another observational evidence of dark matter. Perhaps the most convincing evidence for existence of dark matter comes from light from the time of the first atoms. So, as you might know, our universe is like a move. When we look far, we are looking also back in the past. So we can look far back enough to the time when the first atom is formed, and we can see the light from that time. This light is called the cosmic microwave background. In this cosmic microwave background, when we look at a region of the sky, there are slight differences in temperature of the light or the color of light that's coming. So this is a false color image. On one side is the actual image that we see of light from the time of the first atoms, these patterns in this light. That's based on the Planck satellite. And if there was no dark matter in our universe, then the picture we should have seen is the one on the right. So you notice it's very clearly evident that this is not the universe we live in. And it's really important for this picture to be true, that it's the correct picture to be true, that this invisible matter doesn't talk much with light. It doesn't interact with light. Hence, invisible or dark matter. So, I told you a few bits of evidence about the existence of dark matter. How is this dark matter distributed? There is a computer simulated version of how dark matter is distributed. This is a really large size. It's not the really dots of light that you see are galaxies and galaxy clusters, right? So this is on a very large length scale. The dark things that you see is supposed to be how dark matter is distributed. You notice that it forms like a filament-like structure. There are nodes where things are concentrated, that's where the galaxies and clusters are, and then there are filaments connecting. So this is how dark matter is supposed to be distributed in our universe. Of course, we can't see it, so we can infer this by different ways, but we can't actually see this distribution done. So I've given you a few bits of evidence about why we think dark matter exists. And it makes up such a large amount of matter in our cosmos, and all of these observations tell you that roughly it's the same amount. So they're consistent with each other, which is why we have confidence that this stuff exists. However, all of this evidence that we have for dark matter comes because of its gravitational influence. So the galaxies were moving too fast. The stuff around galaxies was moving too fast. But all of this evidence is all coming from gravitational interactions. So that's great and fine. Okay, so that's something we know, but we have to keep in mind it's all coming from gravitational interactions. The problem with this is that gravity is pretty democratic, right? It treats all particles equally. It doesn't care whether you have charge, you have mass, you have spin. It treats everything equally. So we don't know much about what this dark matter is made of. We know it exists because of its gravitational influence, but we don't know what the microscopic identity of this particle is. What do I mean by that? We don't know what the mass of this particle that makes up dark matter is, what is the charge, what is the spin of this particle, and how does it interact, even if weakly, with other matter. So we don't know much about this particle, even though we know that a lot of this dark matter particles exist. So let's try to put some numbers here. So when I say we don't know what it is, but we do know something about what it cannot be. So for example, we know quite well that dark matter cannot have a large amount of charge. So E is the charge of the electron. For a certain mass range of the dark matter particle, the charge of the dark matter has to be at least 10 to the minus 6 times smaller than the charge of the electron. So it's not very charged, and this seems consistent because it doesn't seem to talk to much. We also know that from cosmic microwave background, as well as from other observations, and more importantly from direct detection observations, that it cannot interact with regular matter. And direct detection means we're trying to detect dark matter on Earth, and we haven't been able to. So from that, we know that it cannot interact very strongly with regular matter. So we have bounds on how strongly it can interact. And then, at this point, we kind of run out of things we can and cannot say. we don't know what the spin of the dark matter particle is. You might, in your physics class, you might have learned that particles come in two flavors, boson and fermions, half integer spin or integer spin. We don't know whether dark matter is a fermion or a boson. Somewhat most embarrassing is that we don't even know the mass of the dark matter. And to tell you how embarrassing this is, let me give you a range that is allowed for dark matter masses. The mass of the dark matter particle can be anywhere from 10 to the minus 19 eV per c squared, right? Or up to 10 to the 19 G. Just to give you a sense of numbers, an electron is a mega electron, right? It's 0.5 MeV. So that lies somewhere in the middle of this. There's this huge range. We really don't know what the mass of the dark matter particle is. So 10 to the 19 GeV, why? Because that's a quantum mass. That's the maximum mass of the particle that's expected to have. We really don't know what the mass is. And indeed, this is assuming that dark matter particles are individual fundamental particles. If you allow dark matter to be made of composite objects, it could be as heavy as a few solar masses. Be similar. So we really don't know what the mass of the individual particles is. So why is this the case? Why is this so unknown? And there's a good physics reason for this. The reason for this is that gravity cares about mass density, not about number density at all. What do I mean by this? So you might remember that this is from Newtonian gravity, this is Poisson's equation, this is the density of matter, this is the gravitational potential. So notice that the gravitational potential is determined by masses. Now, mass density of dark matter is made up of the mass of individual particles times the number density. For gravitational influence, what we know is the mass density. Now, we could make up the same mass density by either making the mass of the particle very big and the number density very small. Or you can make the mass very small and number density very big. The influence as far as gravity is concerned will be the same. So that's why, because all of our information about dark matter so far has come from gravitational interactions, we only know about mass densities. So the mass of individual particles is quite few. So that's why there's such a large uncertainty in the mass. So let me put this sort of on a scale here. So here on the bottom axis is the mass of the particle, the electron volts, from all the way from 10 to the minus 22 eV to 10 to the 19 GeV. And here I've roughly drawn the bounds that we have on this particle. I'll explain as we go along why there's a bound and the dark matter cannot be lighter than a certain number, even though it's a very small number, it's still a bound, and why it cannot be heavier than a certain number. So the mass has to be bounded with these two bounds. So the mass is not very well constrained. Now let's move to the next property that I haven't said much about, which is about the spin. And you'll see that there's an interplay between the spin and the mass of it. So talking about the spin of any particle is talking about a social life. So fermions don't like to hang around each other. There's the Pauli exclusion principle, which tells us that no two fermions will occupy the same quantum state. So not too many of them want to sit together. On the other hand, the other types of particles we have are bosons. Bosons are types of particles that have no problem sitting on top of each other. They like to collect on top of each other. They're happy to hang around together. So fermions knew about COVID way before we did, right? And they were like, okay, we're not hanging out together. Let's be separate. Bosons have no such problems. And of course, it's important, as I'm sure you all know, bosons have an important history, which is based here. The idea that there could be particles that would behave fundamentally different from what we were used to in terms of electrons and protons and so on was discovered by Sapien Bose in his attempt to understand the behavior of light. So he had discovered this whole new important class of particles, which includes light, how they behave, the fact that they can sit on top of each other without it. And it's truly, I'm sure, again, you must have heard all of these stories. It's amazing that he, as a young reader, right, when he was at Dhaka University, he wrote this letter to Einstein saying, "You're going to figure out, would you mind sending me for publication?" And it was amazing that, Einstein took it seriously, he read it, he went ahead and submitted it for publication. Later on, as we'll see, Einstein and Bose would again make an appearance together. He was later at that. Okay, so we've got these two types of particles, bosons and fermions, and what do they have to say? What do we have to say about these in the context of time? So as I told you, we know the mass density of dark matter, and we want to make that mass density up with the help of a mass and number density. Now, if you have fermions, then you can't put too many of them together. As a result of which, this puts a constraint on, that means that you can't make the number density such, so you can't put too many of them together, so there's a bound on how large the number density can go. This in turn translates into how small the mass can be. So this combination, because of Pauli exclusion, tells me that if dark matter is a fermion, it has to be heavier than 100 electron volts. This is an amazing shift from what we started with. We said dark matter mass to be 10 to minus 19. Right? If you make an additional assumption it's a fermion, then this assumption immediately tells you that the mass has to be bigger than 100 eV. So clearly mass and spin together are telling, if you know something about both of these things, you learn something about it. On the other hand, if dark matter is made up of bosons, then this limit goes away. So we have no such limit that the mass of the dark matter particles has to be heavier than 100. Now the mass can be very light. And as you make the mass light, according to quantum mechanics, when you think about the size of the particle, it kind of becomes bigger. The Compton wavelength is 1 over the mass. So it becomes bigger. In particular, the de Broglie wavelength is also bigger, as a result of which, if you put too many particles in one region, they have to be sitting on top of each other. They are not separate from each other. Once you make the mass sufficiently light that so many of them are sitting on top of each other, they lose their identity. You can't tell one particle from the other. They all have to be sitting on top of each other. And what happens is that in this phase, now you stop talking about individual particles and you talk about a classical field of these particles. So in this regime, particles lose their identity and it behaves more like a classical field. Again, it was important that these particles be bosons for this to happen, because fermions would stay apart. It would never be it. So once dark matter is boson and sufficiently light, it starts behaving like a classical field. Now there is a lot of fun to be had in terms of trying to figure out how it will behave in our cosmos. Because once it starts behaving like a field, there are new phenomena, especially a nonlinear field, such as interference. You'll be able to form nonlinear waves in them. You'll be able to form these fascinating objects for solitons in them. And all of these things we can look for in astrophysics. So new signatures we can look for. You will find that many of the things I'm talking about, your classes or research is that if you condensed matter, you will see a lot of similarities in some of these ideas there. That's where the fluid mechanics as well. You'll see similar ideas emerge there. So let's put in some numbers to give you some sense of what we are referring to. If dark matter is a boson and it's sufficiently light, then the number of particles in a de Broglie volume, which is a measure of how densely packed these things are, for a mass of 10 to the minus 5 TeV, which is a very popular particle called axion, which is also a boson, would be 10 to the 23. So it's very highly occupied. So there are lots of things on top of each other. If you make the mass even lighter, then it would be 10 to the 83. So it's so many of these particles sitting on top of each other that we lose our dip. Similarly, the de Broglie wavelength, which is something quantum mechanical that you think about, although it can also be thought about in a different way, the de Broglie wavelength for these light masses can be so large that it can be macroscopic size, meaning you can have a de Broglie wavelength that's about a meter or even light years in extent. So now you can see these wave dynamical effects that we are not used to thinking about for fundamental fields. You can see these effects on very large length scales. And I want to make a slight distinction. These are wave dynamical effects. Arguably, it's not truly quantum effects. They're effects of wave dynamics, not really about true quantum effects. So this is the part that makes this looking at wave dark matter interesting, because these wave effects can now be observed on astrophysical fields and we can look for. So without keeping you too much in suspense, let me give you a demonstration of what these effects would look like. So this is a computer simulation of how dark matter would cluster together to form things. So on this side, it's a dark matter only simulation. Sorry for the change in color from before. Here, light colors means more dense, dark colors means less dense. So here's what a simulation of how stuff connects together in dark matter shows. You zoom in, and this is a zoom in of that region. You zoom in further, and this is how clustered. So this is for a dark matter particle candidate which is heavy. It's not true light, right? So the wave effects are not present. This is how density would look like in dark matter. Here is the same picture, but now with a very light dark matter particle, where wave effects are important. So notice, if you can compare, it's a little bit dark on the top, but if you can compare on the top, notice that there's a lot less structure compared to previous case. So it smooths out structure on some scales. If you zoom in on these regions, you will find these patterns, okay? These light and dark patterns. Can anybody guess what if this is behaving like waves? Why is this light and dark pattern there? Interference, right? The fundamental thing about waves is that they interfere. We are just seeing interference patterns in the distribution of that. Well, these are wave effects that we now see on very large lengths, and we can try to look for this. Again, we haven't seen this, these are real simulations, right? We haven't observed these yet. But this is what we will try to do. All right, so this was somewhat of an introduction and a little bit of detail. Let me pause. Any questions about anything so far? Yes.
Very nice.
Yes. Good.
So I have a very nice question. So if dark matter waves behaves like waves, so does the interference pattern really matter here in the signature of how they attract, like the attractive potential? If we are going to consider attractiveness or repulsion or something like that, does the interference pattern play into that?
So a great question. So of course, this wave-like dark matter still has gravitational interactions. And there's attraction as goes on. What interference does, we go back sometime. So what interference means is that there are some regions where dark matter will have zero density, and some regions where it has a large density. Right? That's what we say. So the distribution of dark matter on those scales is much bumpier. And there's very little dark matter here because you're in the dark fringe, and a lot of dark matter next to it. So it creates a slightly more bumpy distribution of matter on these scales because of interference. So the attraction is still there, the distribution is different. And we will see that observationally we can look for that. We can look for the bumpiness in the dark matter distribution on these scales with the help of stars and other probes and see if we can. Okay. Let's move on. So now I want to tell you a little bit more about the different kinds of things that can happen in wave dark matter. And you will see that I will connect the wave effects of dark matter also with the spin of dark matter. And if the spin 0 particle or spin 1 particle, still bosons, you can't do waves like this with fermions. But within bosons, whether it's a spin 0 particle, scalar, or a vector, I will connect with that as well. Now I'll tell you the different things that can happen. We may or may not get through all of these things, but we'll see. For I know that many of you are also mathematical physicists or mathematicians, so let me sort of ground. So far, I've just been talking to the pictures. Let let me ground this in a particular model so you can sink your teeth into it and know what I'm talking about. So wave dark matter, if it's a scalar field, if it's a spin zero field, it can be described by what is called a time coordinate equation. The action for the time coordinate equation is written here. So chi is a scalar field, so it's the metric. This is a Ricci scalar, which is takes care of gravity, and it's the mass of the part. Now, one thing which is important about dark matter is that it cannot be moving too fast. Why can't dark matter be moving too fast? Because if it moves too fast, then it has too much kinetic energy, and it can't clump in the way we need it. So because it's not moving too fast, it means it will be non-relativistic. So we don't have to do a full relativistic treatment of fields. We can get away with non-relativistic treatment, which is a lot easier. So what you do is mathematically you take your fully relativistic theory and you separate out things that are moving very fast from things that are moving very slow, and you figure out how the slow part behaves. For those of you who have taken some quantum mechanics, this is similar to what's called the WKD approximation. So you've heard about this, you might have heard about the WKD approximation, it's similar. So you do that, and once you take the limit, you will find that the equation that you need to solve is what looks exactly like the Schrodinger. So notice this chi field, which is relativistic, you take a slow part, which is a psi, and a fast part because of the Hubble frequency, yes, and the psi field, slow part, satisfies the Schrodinger equation. But there's something interesting. In the Schrodinger equation, there is a potential here, which usually we call the external. But here, this potential phi is determined by the field itself by the boson equation because it's a slant. So even though it looks like the Schrodinger equation, it's not. It looks exactly like it, but this phi depends on the field itself, so it's highly non-linear. So this cannot show the equation looks linear. This is not linear. Yes.
It's like
yes. So the question was, is this a self-interaction? It is a self-interaction, but it is in a nonlinear Schrodinger equation. The self-interaction term would just be psi squared psi. This is not exactly psi squared because we have to invert the Laplace. So it's a long-range interaction because it's gravitational interaction. The self-interaction term usually in the nonlinear Schrodinger equation is this point interaction. So you get a Schrodinger equation which you need to solve, but it's really a Schrodinger and a Poisson equation together that we use. So that's not scalar. What about, I told you that we want to think of other spin as well. So what about a vector field? So again, we write down the relativistic action. It looks essentially like electromagnetism, except that there is now a mass term. It's dark matter, it has to be non-relativistic, so it needs to mass. Do the exact same. Don't worry if you're not following the mathematical details here, but for those of you who are interested, you can do the same procedure with vectors as well, with the spin one field. And again, you will get a non-relativistic version of it. And that non-relativistic version again satisfies the Schrodinger equation. So previously in the Schrodinger equation, we are used to seeing psi as a one component object. Just say it's a scalar. Now it's a three component object because it's a vector field. So it's three components for the three spatial components of the vector. Again, this is an equation. This is a Schrodinger-like equation. This is a Poisson equation. Together, if you solve them, you will be able to get all the phenomena for that one. There's something quite important when you go from scalars to vectors, that is from spin 0 to spin 1 fields, which is that scalars or spin 0 fields don't have intrinsic spin angular momentum, whereas vector fields can have intrinsic spin angular momentum. So now this field, if you make it a vector field, will have spin angular momentum in the system. And we'll see the effect of that in this interaction. Just to give you some intuition about the spin angular momentum, here is the arrows represent a vector field. You will see that at each location, the vector field will be moving in an ellipse. The fact that it's not moving in a straight line back and forth is telling you that there is spin angular momentum. Here is a video. So the field at each point is doing these ellipses. And if you were to calculate the spin angular momentum for every time the ellipse is not aligned, you would have some spin angular momentum. Okay, so now I've given you the models of scalars and vectors, spin 0 and spin 1 fields for dark matter. Let's see how do we distinguish them. I want to distinguish them from observations. So how am I going to try to distinguish them? So we've already seen interference being the important property of waves. So let's see if we can use interference itself to see if we can distinguish variance. This part is nice and almost embarrassingly simple. Right? So hopefully I can convey the idea. So if you take two waves that are scalars, right? So two waves in the same field and you superpose them together. The interference means that when we add waves together, the sum, the square of the sum is not the sum of the square. This is what wave interference means. So this bit right here, you add two amplitudes together and you take the absolute value square. It's not just a square of individual pieces because there is an interference term. So whenever you add two waves together in the same, and it's a scalar, so that there's no other direction to add them in, then you will always have some interference. On the other hand, if it's a vector field, you can put one wave in, say, the vertical component of the field, and one wave in the horizontal component. So this wave like this, and this wave like this, they're both waves in the same place, but because they're in different components, they don't need to interfere with each other. So you can see from this simple example that if you have a vector field, the amount of interference generally will be reduced compared to if you have scalars. So here is a visual representation of that. So imagine that we have taken a bunch of scalar waves and added them together with random amplitudes and phases, then we will see that the density of the sum of squares will look like this blue curve. So notice it goes to 0 and it deviates from 0 quite a bit. On the other hand, if you take vectors and add a bunch of them together, then notice that the deviation from the mean is much less. There is less interference. Interference allows you to go to 0 as well as very large amplitudes. You reduce interference, you kind of stay in the middle. So interference is reduced when you have vectors compared to scalars. So this is one way you could go if you look for this in our observations. Here is a look at this in a slightly more pictorial realistic way. So here I'm showing you the density of dark matter when you take a bunch of waves inside a halo of dark matter and superpose them. You notice a contrast that is dark and light, right? These are interference. If I now go to a vector, which is a three-component field, you still see them, but you see that the contrast is reduced, right? Because there's less interference. By analogy, I can extend it not just to a vector, but to a tensor field, so a 5-component object. Again, you see some bright and dark splotches, but it's much more reduced. So interference goes down as the number of components goes up. And it just scales by the number of components. So if S is a spin of the particle, 2S plus 1 is the number of components. So this contrast reduces as you increase the number of components. You can see this, this is just a snapshot of what we created, but you can see this emerge more dynamically. So you're seeing, you start out with some blobs of dark matter and you allow them to come together. So it's a numerical simulation of these things merging together under gravity. You can see both, they look very similar, right? Both sides of those. They look very similar. But one of these is a vector dark matter field, and one of this is a scalar dark matter field. And if I have done my job right, hopefully some of you will be able to tell me which one is a scalar and which one is a vector. Okay. Anybody want to take a guess? Sorry, go ahead. Yeah. Which? Okay, why? Exactly, right? So it's even evident to the eye,
when you do these simulations, that one is a scalar, identical initial conditions, but you can see it's just interference, right? Okay, so now I feel good that at least I've done a good job. That I'll take credit, even though you actually understood what I said. But I'll take credit for doing a good job. Okay, so thank you for that, right? So it's clear that these interference effects matter when you go from one spin field to the other. Okay. Here is just sort of a snapshot of that same phenomena, right? Just showing you this is in spin 1 or vector field, and you just saw that, and this is in a scalar field, and you saw the difference between the two. Okay. How can we, I've been telling you that we might be able to distinguish between the two, so how will we be able to tell? How do we detect interference patterns? We can't see this stuff. We can only know about this stuff gravitationally. So how do people expect to look for these interference patterns? So the way we do this is the following. Right? So imagine you have some dwarf galaxy, which is it's a very light galaxy, which doesn't have too much regular stuff. It has stars, but it doesn't have too much gas in it, and is dominated by dark matter. Okay, so the gravitational potential is dominated by dark matter. Now, if you have interference effects, then the distribution of dark matter is a little bit wobbly, right? There's more here, less here, more here, less here, more here, less here. So now when the stars are moving in this region, they see the bumpiness of the gravitational potential. So as they're moving, if the distribution of dark matter is bumpy, then the stars also don't move in a smooth orbit. They kind of get a little bit of kicks as they move around. Okay? So this causes an increase in the velocity dispersion of stars in these systems. So we look for the velocity dispersion of stars in these systems and try to ask, is it consistent with the distribution of dark matter being smooth, or does it require it to be bumpy? Okay. The fact so far, we have found that we don't need this extra bumpiness that is there, so it gives you a bound on how much interference there is. Okay. Now, interference comes in detail. The length scale of the interference depends upon both the mass of the particle, whereas the amplitude of this interference also depends on spin, because more spin means less interference. So you really, when you take the observations, you get a bound on the combination of spin and mass of the particle. Okay, so that's what we have learned. So one of the statements I made in the beginning of the talk, which was about dark matter particle has to mass larger than 10 to the minus 19 eV, that was coming from this type of observations. All right. You can use the same idea of interference causing a little bit of bumpiness in the gravitational potential to also constrain the mass using gravitational lensing. Okay, light, when it propagates through this region, can also get a bit distorted as it propagates through. So you can look at faraway objects which are very collimated, like jets from active galactic nuclei, and you can see whether the images are wobbly or they look pretty collimated. Again, using the same principles that we use with stars, you can put bounds on the mass of the particle this way. In reality, on the combination of mass and spin. Okay. So that's what astronomers have done to give some limits as well. This is a little bit more on, this has not yet been tested observationally, but depending on the spin of the dark matter, the shape of the dark matter halo, meaning how the density is distributed, okay, also changes based on the spin, and if you're interested, I can tell you more about this. Okay. So I've told you a little bit about this interference effects. Now let me tell you a little bit about how structure grows based on spin. Okay. And this, I'll be quite cursory. If you're interested, there's new work that is perhaps more up to date, but I'll start with things that are visually more interesting to see and then go into the more technical sides. Okay. So you've seen this image before. I showed you a static image of this. What you should think about this is that this is the density of dark matter inside a dark matter halo, so towards the center of the dark matter halo. And you see these interference patterns. Okay, they are there. But this is a static image. I'm going to now allow this to evolve with time, meaning this is a numerical simulation of the Schrodinger-Poisson system. It's just solving partial differential equations on a computer. And you'll see something interesting happening. So this is all running on the same time scale. Okay? And you'll see something happen first on the leftmost side. Okay? You notice that there was no real pattern at the beginning, right? It all looked like pretty random interference patterns. But suddenly, this object grew in the middle. This object that formed it's a blob, it's an extra density of dark matter that emerged naturally, right? Just from this random collection. Something else seems to be happening in the second frame as well, right? But you wait for a little bit and you'll see that something very similar just happened there as well. Right? That again, a blob emerged there too. Has anything happened in the third frame yet? Nothing yet, but patience, right? Patience for this as well. You see something beginning to happen there as well, right? So same phenomena seems to be happening regardless of the spin, but there is a difference. It happened first here, then here, and later there. Right? So it seems that this interference effect that we were talking about also influences how quickly these blobs form. Okay? So here somehow the higher the number of components, meaning when you go from a scalar to a vector to a tensor, it takes longer for these blobs to emerge. Just a little bit more quantitative here. By the way, I should mention, since I know many of you are undergraduates here, so this work was actually led by two of the undergraduates here, Visha, who you will, it's hard to forget because his name is hard to forget. So actually you can read his Thai, his Vanishvecharungruang, right? So him and Jonathan Thomas, they led this effort, right? So they are the ones who did these simulations to verify these predictions. So I'm really proud of having collaborated with them. And Mudit Jain was a postdoc who was a lead author on the study as well. Okay. So I went the wrong direction. Okay, so here is a little bit of a more quantitative description. So this right here is a maximum density in that box that you are seeing. It remains what it is for a while, and then suddenly those objects emerge, so the density goes up. Right? But you notice that the scalars emerge first, then a while later the vectors emerge, and a while later the tensor object emerge. Right? Notice that this is 1, this is 3, this is 5. So basically the time scale is proportional to the number of components. So this is a nice way simple way of understanding the result. The number of components just determines how long it takes to emerge. If you're interested, I can tell you there is a nice calculation of how you can figure out how long it takes for these objects to emerge, but you can ask me if you're interested. Okay. So I showed you these blobs, but I haven't given them a name. These particular types of blobs are for me, they're amazing objects. Right? These objects are called solitons. Okay. Has anybody here heard about solitons before? Okay, great. So I'm happy to be the person to tell you about it. Okay. So these objects, as I said, are solitons. So what are solitons? So let me give you a sort of historical overview. Right, so in 1830s, John Scott Russell, right, was in Edinburgh in England. He was riding on his horse next to a canal with a boat in it. Right? And this boat came to a very quick stop. And when it came to a stop, it generated a pulse in the surface of the water. Right? So it's like, a giant pulse. And you must have seen this in rivers, right? Something comes to a stop, it generates a pulse. Usually you will find that these pulses, once they're generated, they just kind of go away. Right? They don't remain as they are. But what John Scott Russell noticed is that this pulse that was created just maintained its shape. It neither became smaller nor bigger and continued traveling without changing shape. Okay? So it was a localized excitation of the height of the surface of water that traveled without changing shape. It maintained itself. This arguably was the discovery of the mathematical thing that we call a soliton. This is the physical manifestation of that. So what is a soliton? A soliton is a localized excitation of a field that moves without changing shape or holds itself together, and what's really happening is that it's some effect that's trying to disperse the pulse, but there's a competing effect, nonlinear effect, that's trying to hold the pulse together. And the competition between the two is such that this thing remains as it is. You might think this is a very odd thing to happen, but this is incredibly common. These objects are found, for example, as John Scott Russell discovered, in water, in canals. This, what you see right here, this is actually the same canal that John Scott Russell had observed this in Edinburgh, where the students of this university recreated it at a later time. So you see this pulse rising there. Okay. Now, this is a sort of effectively a 1D object because it's only variation in one direction. We are talking about a full three-dimensional thing, but still the same physics applies. It's amazing that these kinds of objects, these nonlinear excitations that move around without distortion, have been found in optics and hydrodynamics, in Bose-Einstein condensates. Again, Bose comes up. All of these things, we have observed these objects. At some point, we were even thinking about using them for communication. Right now, people are possibly even thinking about them for quantum computation as well, because these are such stable things. Okay. Unfortunately, for the field that I am in, many times they have been hypothesized, but we haven't found them yet. So lots of fields that we think about have these objects in them mathematically, but we haven't found them in nature yet. So let's try to think, even though we haven't found them, we still have hope that perhaps if these are in dark matter, we can detect them. So let me tell you a little bit more about their properties. So these solitons, when you think of them as a field, the types of solitons we are talking about, the field is in some localized region and it's just moving up and down. It's just oscillating, but it neither goes out nor in. Right? It's not like a ripple that moves out. It just stays in place. Okay? So again, ignore the mathematical details for the moment. All it is, it's a blob that gravity is trying to pull it in. Because it's a wave, the wave is trying to disperse, but the balance between the two holds it together. Okay? So that's how a soliton in this structure is formed. You can solve for this. You can find out mathematically what these objects are, but we'll ignore that. So that was for a scalar, meaning a scalar field just doing its thing, oscillating in place. Now let's think about solitons in a vector field, because remember, one was a scalar, one was a vector. This part is, in recent years, this has fascinated me a lot, right? I've been really excited about this. So when you think about a soliton in a vector field, it's still a field in some sense oscillating, but because it's a vector field, it needs a direction, right? It's not just a scalar, so it needs a direction. So you need to point the vector somewhere. So one possibility is to point the vector just everywhere it points up, and with time it flips back and forth, right? That's one option. This is linear polarization. You're used to this in light as well. The other possibility is to give the vector a circular polarization, meaning it moves in a circle. Okay? There are other options as well, which are linear combinations of the two, but these are two bases that you can work with. The interesting thing here is that if you have this linearly polarized system like this, then the spin angular momentum of this object is zero. Again, if you've taken electromagnetism, and maybe you haven't covered this, or maybe you have, light can also have angular momentum. Right? Linearly polarized light has zero angular momentum. Circularly polarized light has non-zero angular momentum. So this is non-zero angular momentum, intrinsic spin angular momentum, and it's a very large amount. It's equal to h bar times the number of particles that are present in the blob, and it's coherent. It's a giant ball of spin. Okay? So it's quite an interesting object that gets created when you have spin 1 fields. And in general, you can have linear combinations of these as well, as I mentioned. Do you form objects with a lot of spin? The answer is when we look at these simulations, we actually see them naturally form. So that's kind of fun that we could, if this is the type of dark matter that exists, then there might be these solitons hanging around the universe with a gigantic amount of spin angular momentum. And it would be interesting to see if we can detect them by different observations. I told you that Bose and Einstein will keep on coming back. Here's another example. Okay, so these things I've been talking about, the solitons and scalar fields, solitons and vector fields, it turns out that even though we haven't discovered them in dark matter, people have discovered solitons in Bose-Einstein condensates. Okay? So they have actually created these solitons in the lab, crashed them into each other, and seen what happens. So it's a nice playground to connect things we can do in the lab with what potentially could be happening in the universe. Okay, how much time do I have? Am I running out?
21.
Huh?
21 minutes.
20 more, okay, that's a lot of time. Okay, I won't keep you that long. So I've told you that the spin part is kind of interesting. It creates solitons, but can you actually see it? It's one thing to say these objects can exist. Can you actually detect it? And this turns out to be hard. But there are some exciting ways to probe it. One way of probing the spin of dark matter is with the help of black holes. So black holes have this amazing ability that if a certain type of field exists and its mass is such that its Compton wavelength is comparable to the event horizon of the black hole, the black holes can act as factories to generate this field. So they spontaneously create this field around them. And the rate at which they create these fields and the type of distribution of this field around the black hole depends on the spin of the particle. So this is one way in which, if this dark matter field exists, black holes might be able to generate them around. So here's a little video of this. Again, it's hard to see what's really going on, but take my word for it that black holes can generate, at least theoretically, we find that black holes can generate these fields around them. This is too much technical detail, but these objects that I talked about with spin, when you think about them in the context of general relativity, you can ask how difficult, what happens, how compact can you make this before they collapse to a black hole? And again, that answer depends upon the spin angular momentum of the system. When you look at two of these objects orbiting each other and you look for gravitational wave signatures from them, again, unsurprisingly, you will find that it depends upon what is the spin angular momentum of these objects. So these are different ways. If we detect these gravitational waves and these objects are sufficiently compact, we can look for these effects in nature. But these are speculative and it's still far away from us being able to see it. There's one more thing. You can also, if you allow this dark matter, a particular type of this dark matter to couple to light, again, it's weakly coupled. It doesn't usually produce light, but when you smash two of these objects together, you can create the right conditions that it sort of goes off. They annihilate with each other and go off into a flash. Okay? So this can also be another way of trying to look for them. Okay. I think I want to sort of also point out that you can't just look for this dark matter in astrophysics. You can also, people have been building detectors on the Earth itself to try to detect these things. And there's a lot of effort going on in that direction as well. And again, the detection strategies can depend upon the spin angular momentum in the system. Okay, so I'm now coming to a sort of towards the end, but give me a few more minutes. So we started this talk with the question, what is 85% of matter in our cosmos? In particular, I have tried to tell you a little bit about what we have learned. Right? I haven't told you what this stuff is, but I've told you how the behavior of the stuff depends upon the mass of the particle and the spin of the particle. But there's something that I have not told you much about, which is if this stuff is there, it must also be produced at some point. Right? If it exists today, it must have been produced in the past. So then there must be a connection between what the history of this stuff was, that is how it was produced, and how it is distributed in nature today. this is too complicated perhaps right now, but a way of describing the distribution of dark matter is through what is called the two-point correlation function or the power spectrum. And this power spectrum, depending on how dark matter was produced and what its properties are, will have different shapes. And observationally, there is a huge program to try to understand how this dark matter is distributed based on that. Indeed, another thing that I sort of haven't gone in detail is that if you produce dark matter, you've had talks recently on inflation, you can produce dark matter during inflation, or you can produce dark matter after inflation. It turns out that even these two possibilities, if you produce dark matter after inflation, even that one statement automatically tells you that it cannot be lighter than 10 to the minus 19 eV. If you produce it during inflation, it can be lighter. So there's a nice connection between how dark matter is produced and what its properties are as well. Okay, so there's a lot more, I think, in this direction, and I am quite excited about exploring this aspect of it, right? This connection between production and what its distribution is today. And so ask me questions if you're interested in this. Okay, so let me sort of come to the end. Right? So I wanted to thank the group that I've given the talk, but of course our work is usually, as you might know, is done by the students, the postdocs, and everybody. Right? So here, I share my group with Andrew Long, who is sitting there, and the rest of the people are postdocs and students. Some of them have moved on, some of them, new people have come in. So I want to thank them, of course, for all the hard work they've done to make some of the results possible that I've shown today. Right? And finally, I'm from this university called Rice in Houston. If you want to know more about it, if you want to know about opportunities there, please come and ask me. Okay? Thank you.